Good afternoon, everyone. When I read the article, the BBC Microbit from the UK to the world in the March 2020 communications of the ACM, I thought, these guys got it right. I've used the Raspberry Pi and the Arduino with students in the past, but did so at higher grade levels in college. If you wanted to introduce computational thinking to a younger audience, it is best to use something that will not overwhelm them, for fear of them getting just frustrated and avoiding it in the future, which would be worse than using it at all. The microbit is just the perfect platform for younger children and extends very well into the older ones. After reading your article, I ordered one and experimented with it. It works exactly as promised. Having ordered it in April, the one I used was the previous version, and after talking with our guest speaker, I realized that it had made it even better, which our speaker will cover. In addition to ordering the microbit after reading the communications article, I also thought that one of the authors, the CTO for the organization, would be a perfect speaker for our group, especially for Computer Science Education Week. Additionally, and although this year has been a hard one to say the least, and our meetings are virtual, our speaker is from across the pond, Oxford. So what better time than now to get him to speak to us? So with fingers crossed, I wrote him. He replied immediately with a definite yes. Thus, it brings me great pleasure to introduce our speaker this evening, Jonathan Austin. Jonathan is the Chief Technology Officer at Microbit Educational Foundation on secondment from the ARM Limited. He was responsible for the ARM's delivery into the original Microbit project through 2015 and has been the Chief Technology Officer of the foundation since its creation in 2016. The title of his talk this afternoon, evening for him, is Using the BBC Microbit to Teach STEM, where he will tell us the story of the device, how it came to be, and then how it is in use today. So without further ado, please welcome our esteemed speaker, Jonathan Austin.
Thanks very much, and hello everybody. I feel like after that introduction, I might as well just skip the first half of the presentation because I think you've covered what the microbit is beautifully. But I'm gonna stick with what I've got here, so as not to throw myself off. So thank you very much. I'm really honoured to be asked to speak at this, and I hope that you find, I know we've got quite a diverse audience tonight, so I hope that in this you all find something that's interesting. I'm going to talk first, I think, about some history of the BBC Microbit, then make sure that we're all on the same page about what it is and who the Microbit Educational Foundation are, because I'm not sure amongst the kind of group whether everyone will have used a microbit. I'm going to cover a little bit about how people are teaching with the device and some of the ways it's been adopted around the world. And then we'll look at introduction to microbit v2 and some speculation and some interest in what's next. So I thought, given the kind of the mixture of some people who are very embedded in the CS world and teachers who are embedded in the CS world, but with a real focus on teaching, perhaps, I wanted to cover four kind of areas. These are themes that will run throughout the presentation. So this is not the table of contents, as it were, but I just kind of want to highlight where we're talking about story, where we're talking about maybe some demonstration of how it works, and you'll get a little bit of analysis as we go as well. So Katie Henry, who works for the Microbit Educational Foundation, is also here. And I think if you have any questions, immediate questions that you want to ask in the chat, Katie, are you okay to kind of follow up with things in the chat just in case? But you know, if it feels like I've gone off the deep end and nobody knows what's going on, just shout and be like, whoa, what are you talking about? And I will pull it back and try and give you some context and come back to something that we all understand. But this is this is kind of, you know, the Zoom format is nice. If people want to ask questions in the chat, that's really great. And I'm going to hand over to Katie a little bit to talk more about some of the regional activity as well. So let's start by having a little bit of story. So I'm going to start in 1981. I'm not going to go year by year since 1981, but this computer was a very important computer for the UK computing industry and for a company that is now very well known called ARM. So some people don't know that the BBC Micro was the computer that sort of brought huge success to Acorn, and then from Acorn grew ARM. And it was a project carried out by the BBC in the UK to put one computer into every classroom in the country, and it had a profound effect on computing education. We still have When we hire into ARM, so as Jan explained, I originally worked for ARM, I'm now seconded out of ARM. When we hire into ARM, it's still really common that people we're hiring say, I got my first experience of programming on a BBC Micro in school, or on one of those other kind of what we now think of as retro gaming computers. But this, you still find pockets of industry, especially the game industry up in Edinburgh and in and around Cambridge, that really grew out of this machine. So in 2015, the BBC wanted to do something in the UK that would have the same level of impact and the same level of significance, because actually what had happened from the kind of glorious, I would say, really ambitious days of teaching computing back in the 80s, where it actually a computer didn't do anything until you coded it, is we'd had this kind of transition from learning about the fundamentals of computing back into things that were much more based around using a computer and computers as tools or as consumption devices. And the BBC wanted to look, to shift that narrative. It also came in the context of a curriculum change in the UK. So in 2014, the UK computer science curriculum was introduced, and that also had this shift away from can we use Excel, Word, PowerPoint, all really important skills, but also to add concepts about computational thinking, algorithms, the way people think and the way computers work. And the BBC looked at the things that existed at the time and said, can we teach a broad audience? Because one of the things that's really interesting about the BBC, they're sort of adjacent to the government, and a very important part of their remit is that they speak to a broad audience. And I said, can we teach computing to a broad audience with this new curriculum? And the answer was essentially no. There was nothing in the market that would reach a broad audience. And so they built the BBC Microbit. And that's this device that I have here. I've picked a green one so it matches my slides, but it actually comes in a bunch of different colors. That's green. Here's a blue one. And we'll talk a bit more about it later, but the color and the friendliness is an important part of it. But it's a versatile programmable IoT device. And what's so crucial about it is it's designed for use in the classroom from the very beginning of the project. And when we're talking to people, we call out these 5 things as kind of key technical reasons that the microbit is effective. And this is actually, I think it's worth saying, this slide, it's got 2020 down the bottom, but this is a slide we wrote in 2015 as we were announcing the BBC Microbit to ARM. So it's got a kind of interesting historical significance. I've tried not to change the slide. I'll tell you when it starts getting new. So easy to program, no installation or drivers. Simple wireless communication between microbits. It's battery powered. So here's a microbit being operated with a little battery pack, which means you can take it and walk away from the computer. It has built-in motion sensors and a display, and that means it's instantly interactive, so people can engage with it straight away. And there are hundreds of sensors and accessories that you can add to it. So that hundreds of sensors and accessories, that wasn't the case as we started. And we say low floor, high ceiling. And now it's available in 70 countries around the world. It's about £10 if you buy a lot of them, which most people are. They're buying it. Either we see people buying a box for their school, but actually we see right up to school districts or countries buying a very large number for the whole country. And it was designed by a coalition of 29 partners. And that is sort of conventionally a total nightmare. People would say, you can't design anything good by a committee, but I think the microbit is a testament to the fact that a well-led, very user-focused committee or coalition actually can design something really unique. And I think it's really significant to me that the microbit was designed by a kind of push and pull of Microsoft, ARM, the BBC, a company called Technology Will Save Us, Farnell, who had the manufacturing concerns. All of that kind of pull and different backgrounds were crucial in making the microbit what it is. And there are now 5 million of them in the world. So the original goal in the BBC was to put 1 million into UK classrooms. And since then, we've now produced another 4 million. So I haven't really told you what it is yet. So I'm going to kind of run through this because you might already know. But I like to draw this analogy between the microbit and a phone. And that's one of the things, phones, every child understands or uses a mobile phone to some extent, but very few of them, before they've engaged with computer science, kind of have a real sense that they know how they work or know what's going on inside them. And one of the things that I think is so powerful about the microbit is that it is the simplest thing that you could say is an analog to a mobile phone. It's got a screen like a mobile phone does. It's got buttons. It's got one button more than the iPhone has on the front of it. So Take that, Steve Jobs. And it's got motion sensors and it's got a radio. So it kind of does many of the things that a phone can do, but yet it's extremely simple. This thing that we call the screen is really just 25 LEDs, and it makes it immediately clear to somebody when they think a bit further about it that a screen is just a bunch of pixels that can be turned on and off individually. So by kind of reducing the phone to its absolute simplest elements, we help people do something really concrete with the device when they program it that helps them understand a much more complicated, more complete piece of equipment in their lives. Still haven't told you what it is. So it's got a display, 5x5 LED matrix. It's got 2 buttons. It's got these input and output pins, space for an external power supply. So these are designed for banana plugs or crocodile clips. And this is a thing we call the edge connector, which I'm going to cover later. We have a kind of distinction between the front of the board, which is the user interface. That's what, when the children's programs are running, that's where everything runs. And the back of the board, which is where the kind of looking inside, but we didn't want to put it in a case. We wanted it to be very visible, very exposed, and have it labels that explained itself so that people felt like we were encouraging them to look at the device. We weren't trying to hide the processor. This wasn't dangerous. This wasn't scary. These are the things that make up your device, and we're being explicit about what they are. So micro USB for programming, a reset button, a battery connector. The main processor on the microbit V1 is a Nordic NRF 51822. It's got a Bluetooth antenna, accelerometer and magnetometer, and this interface processor, which I'm going to talk a bit more about later when I talk about how the microbit really works. So I mentioned this edge connector. That's a kind of bunch of contacts that the board can plug into, and it allows a whole range of accessories that the microbit can easily connect to and talk to. So it extends the microbit beyond what the device is and can do itself. So if we look, I used to have a slide of accessories, and now I've had to kind of expand it over a whole scroll of many slides, but there are now more than 250 accessories. Actually, I've got a slide in here that says 200, and I realized that I need to update it. It says 2. Right, so one of the key things about the microbit is that it is a USB drive. When you plug the microbit into a computer, it's a drive called microbit. And that is key to the lack of installation of drivers, of software. It makes it very easy to program. So you can see here I've got my microbit drive, and I can just drag and drop a hex file, which is the code that runs on the device, onto that drive in order to program it. And that's all you need to do to program it. It copies over. And that hex file can come from anywhere. It can come from an email, it can come from a web browser, or it can come from a native code editor as well. And so the most common place that those hex files come from are 2 web-based editors, one called MakeCode and one that we call the Python editor, which uses something called MicroPython. But there are a very large number of third-party editors, including Scratch, that have other interesting ways of interacting with the device. And I think with some of the DNA of the original BBC project with 29 partners, and also learning, I think, from the way ARM operates, having a very large ecosystem of partners that support the core product or integrate and use the core product, the Microbit Foundation continuously works in partnerships. So we have more than 200 accessories. My video window covers my numbers. We've got at least 16 third-party editors, 1,000 testers on our testers list, 800 developers on Slack. There's a more kind of tech-focused view of the ecosystem. We've done 15 student projects, 571 translators, 150 approved MakeCode extensions. So all of this is about the kind of scale of the microbit ecosystem, which the microbit and the Microbit Foundation alone are insignificant, really, compared to the impact that comes from this huge ecosystem of people around us. So that's a good time, I think, to pause for a moment and have a little demonstration. So I'm going to switch what I'm sharing. You can all take a pause, and I've been talking quite quickly, so catch up while I switch to a camera. In fact, I have to switch camera here. Hopefully you can see my desk with a USB cable. Can someone nod if you can see my desk? What would normally be my camera view.
We can see it.
Yeah, great. So you've got my desk here, and you've got MakeCode. So this is the MakeCode editor in the browser, and I'm going to do a really, really simple project. I'm going to use the buttons. So in input, when button A is pressed, I want to do something. I'm going to grab a block here. I'm going to show an icon. So if anyone has used Scratch before, I think probably for this audience, Scratch will be familiar to everybody. This is very similar to Scratch. You've got a simulator of the microbit, you've got a list of blocks, and then you've got your code area. So when I push button A, I'm going to show a heart. And when I push button B, I'm going to show a different picture. So let's grab. We've got some predefined icons. Let's show a smiley face. But I could also draw my own picture if I wanted. I can show a smiley face, and then let's sort of make the eyes light up. So we do a smiley, and then we do a smiley with eyes lit up. And I can test this before I deploy it to my microbit. I can test this on the simulator here. So if I push button A, we'll see a heart, and if I push button B, we're going to see my little animation of a device with eyes that light up. And you know, the 5x5 display is extremely simple, but watching kids draw things on the display and kind of add meaning to them. One of the first things I ever saw someone do was draw a picture of a dog that you could tilt the microbit. Actually, let me finish this first. So I'm going to start by plugging my microbit in like that. You can see we've got a little light on the bottom that tells me it's on. I click download here. And that's going to compile my program. It's going to be called microbit duck for reasons related to me not changing that name. But I've got my hex file here. I can show that in my file browser. And if I drag that onto my microbit drive, you'll see that the LED on the back of my microbit flashes, and that means the code is being updated on the microbit. And when it finishes flashing, copying over, you hear the sound. So it does, as instructed, it does nothing until I push one of these buttons. So if I push button A now, we see the heart. And if I push button B, we see my little smiley animation. I go back to the heart and back to the smiley. But we've got you know, other things like motion sensors here. We can measure the acceleration. We've got a shake block. So there are lots of different ways to interact. And I'm in the interest of being able to sort of show you more about how the microbit works. I'm going to let you explore the editor with its simulator kind of at your own pace later, rather than go through too much demo now. And there are lots of kind of online tutorials and resources that go through the editor. I'll just quickly show you that we've also got a Python editor here. I've got some code loaded for later, but this is what the Python editor looks like. Right, so we'll go back to the slides and hopefully back to me. Katie, did you want to add something? Or?
Yes, I just didn't want to distract you while you're making that transition to the slides. We have a question in the chat about using Wi-Fi. Does the microbit support Wi-Fi?
So no, the radio on the microbit it's a Bluetooth radio, but we've also written a low-level radio protocol that is broadcast very easy for the classroom. There are accessories for the microbit that allow it to talk to Wi-Fi routers, but the device itself is focused on that kind of educational scenario. So Bluetooth is useful for updating the device over mobile phone and for the radio communication. I'm actually going to talk a little bit about that shortly. So there's our demonstration. And we're back to a little bit more story. So we kind of said 2015, we had the BBC doing the BBC microbit. And then in 2016, the BBC is a broadcaster. They have an education division, but they're not technologists, and they never intended to run the microbit project for the long run. So in 2016, the BBC got together with a number of the kind of key partners from the original project. So ARM, Amazon Web Services, British Council, IET, who are the Institute of Engineering and Technology in the UK, Lancaster University, Microsoft, Nominet, and Samsung. And that group of people said, yeah, we think it's important that this isn't just a one-time thing with 1 million devices in the UK. We want it to have a life beyond the UK project, and helped establish the Microbit Educational Foundation. And our mission is to inspire every child to create their best digital future. And I want to unpack this a little bit, because we've as with kind of vision and mission statements, we've made every single word matter. So inspiring is totally key to us. We think that part of what we want to do is get people excited about technology. This is not just about learning. This is about being inspired by the incredible things that technology can do and the way it can change lives. The next word, every, is so important because one of the things the original project set out to do was increase the breadth of people studying computing. There is There's not a lot of diversity in the computing industry, certainly in the UK and in lots of countries around the world. There are some places where there really isn't a kind of significant gender diversity issue, but there are other kinds of diversity issues. But actually, at the moment, in a lot of the computing industry, it is not very diverse, especially from a gender point of view. And we want to make sure that everyone is getting inspired by computing. We're focused on children, and we're also focused on creation. So we don't want things to happen on rails. We don't want things to be extremely prescribed. This is about people's own vision and their own actualization. And then their best digital future is it's a kind of clear statement that says, we don't know what technology needs to be and needs to do for the future. We can't presume to know that, but we want the generation of people that we inspire, the diverse, brilliant generation of people that we inspire to be the ones that define the digital future, rather than a small, narrow section of society saying, we know what the right thing for technology to be doing in people's lives is. So it's a single sentence, but for me, it's really important. And I think we kind of broke it down into some other points about the mission and kind of how we operate. And these are on the microbit.org website. I think I don't want to go into too much detail, but I think, you know, there's some that really stand out, that we want the microbit to be the easiest and most effective learning tool for digital skills and creativity, and that we work in collaboration with educators to create and curate these exceptional experiences, material and training resources. It's not, we are a very small organization. We're kind of 20 people, depending on how you count. And there's no way that we can service all of the diverse education systems, the different curricula, the different ways the device needs to be used. And so by kind of providing a substrate on which other people can build amazing things is a key way that we want to function. So I wanted to kind of show you then a screenshot from microbit.org. One of the things we do is we've got this projects page, which has a huge range of exciting projects that showcase how the microbit works in it. And we've got instructions that talk you through all of those things. And we also have a whole set of lessons. So we've got lessons aged at lessons pitched at different age groups that cover different areas of the microbit device and different areas of the curriculum. So you can find those on the lessons from the header. I'm going to walk through the website shortly, so just to kind of show people where things are. And I think this, although I am now regretting the color scheme of this slide, I think it's a really important sentiment that education with the microbit is about kids inventing things and expressing themselves with technology as a tool. The idea and the expression has to be first. Technology has to be the thing that allows them to achieve what they want to achieve, rather than you are going to learn about computing today. It's you're going to do this thing you care about, and computing is going to be the thing that enables you. And this slide, when I very first wrote it back in 2017, I think, said inventing things and solving problems they care about. And I went to speak to a couple of people at the computer lab in Cambridge, and they said, you've already closed down about half the people who don't see the world as problems. Johnny, I know you're an engineer and you might see the world as problems that need to be solved, and that's great, but a lot of people don't. And so I think even that kind of making sure that in everything we do, we make sure the language we use and the way we kind of thinking we expose people to doesn't presuppose a bunch of things that shut down engagement and people's sense that this is for them. And I think motivating it by things people care about is really important. Yeah, and I think for me, making sure that children feel confidence and ownership of their technology is absolutely crucial. I don't think we can have, you know, with how pervasive technology is going to be, we can't have a high functioning society if people don't feel confident and have mastery of technology. I think there's too much influence that it can have in our lives if we feel totally beholden to it. Okay. So at that point, I think it's worth just quickly jumping out to microbit.org and having a quick look at the shape of the website, so we can have a look, you know, for teachers that want to find the resources, it's useful just to show where they are and what's available. So we've got kind of two major places that you might want to look here. Projects, that's not where I want to go, projects or lessons. So if we start with projects, we split this into two kind of areas. Make It, Code It is the screenshot that I had in my slides. These are quick projects. You can filter by which kind of language or programming system you want, or which topic you want. So let's say we want to look at physical education. So we can look at physical education and we can see 3 different kinds of step counter of varying complexity as we go. could take off physical education and we could look at networks. So then we've got some interesting examples. We've got a teleporting duck, which hopefully we'll have time to talk more about later, rather than just leave you hanging about what on earth a teleporting duck is. And then if we go back a level, back to projects, do your bit is a really key part of this idea of making things that kind of, or exposing big challenges and really important things about the world to our audience and saying, you're the people that are going to need to solve these problems, and technology is going to be a tool that does it for you. So we can cover more about the Do Your Bit and the Global Goals Challenge at the end if there's time. The next section, which is really great for teaching with the microbit, is this sort of area of lessons. So again, you can choose whether you want MakeCode or Python lessons. And then these are full units of work that are kind of curriculum linked and have microbit code examples, downloadable PowerPoints for them. So if we have a quick look at the data handling one, we've got a kind of breakdown of all of the lessons. You can download a whole bundle of all of them. And I'm going to talk a little bit later about our microbit classroom tool, but where we have code examples, which I think, if I go back to the summary, maybe back to data handling. So you can see in the overall view of the lessons, you can see where we've got code examples. We have this little microbit face. So if we take the treasure hunt, then we've got code available for this one using sensors, and we render the code in a moment when my connection catches up. And you can open this in Microbit Classroom, which is our classroom tool that helps teachers and students connect their browsers together to collect up the work and help the teacher see what the students are doing. So that's a quick look at the website. I'm also just going to make you aware of the impact section, because it means I don't have to switch back to the website later when I talk about it. So here's the impact section, which you're going to be able to look at. Okay. So that is a whistle-stop tour of what the microbit is. And I think that's probably a good place just to pause to say, is anybody feeling like, actually, it's unclear, what the hell is it? What have I missed, Katie, in my kind of rush to communicate what the device is and what we do?
I don't think anything's been missed. We've been having conversations in the chat about learning materials, and teachers are sharing how they use the microbit in their schools in New Jersey. Amazing.
I mean, now I want to look at the chat, but I think I'd better save that to the end. So this is where I'm going to take a bit of a tack down. You could say I'm going to indulge myself slightly and look at some of the kind of technology behind the microbit, because I actually think that partnership that came together and built the microbit built some really interesting, quite remarkable things. So, and I think for a kind of for an audience of computer scientists, there's some stuff, I'm not going to go into too much detail, but I want to call out the areas that you can go and explore to learn more. So firstly, tech.microbit.org is it's a mixture between a wiki and a data sheet. We try and keep it kind of authoritative, but we want people to contribute to it and extend. And it writes up really the details of the software environment for the microbit. So the first thing I want to talk about is the device abstraction. So one thing that I think is really important to, when you want to enable an ecosystem of people to do interesting things with the device, if you're going to have 9 different editors and you're going to have 200 accessories, I think it's important that we're also driving a level of consistency as well. And if picking up a microbit and using it with 2 different editors gave you a totally different experience or a totally different level of abstraction, that could be quite disruptive to learners' ability to move between these environments. And so one of the things that's always been in the microbit project is a device abstraction layer. And I've typoed Lancaster's name, which is extremely embarrassing. I apologize to Lancaster University, but it's spelled correctly here if you want to know how to spell it. So we've got this device abstraction layer courtesy of Lancaster University, and it builds on top of a bunch of other components. The Nordic SDK, the Nordic microcontroller, is the main microcontroller on the board. And for those that are interested in these things, that's an ARM Cortex M0, and on microbit v1 that's running at 16 megahertz with 16K of RAM and 128K of flash, so 258K of flash, but 56K of flash, but 128K of it gets consumed by the Bluetooth stack. So it's a very constrained device. It's a Jan talked at the beginning about the Raspberry Pi and the Arduino. It's much more in terms of kind of computing scale on the Arduino end of the spectrum, whereas a Raspberry Pi is a computer. The microbit is a kind of peripheral device. But I think an important difference between microbit and say Arduino is that the microbit has enough things on the board that your first experience is not plugging it into a breadboard and trying to connect LEDs or trying to connect wires. We try to make sure that that's a kind of secondary experience that you have once you've already had success. We're really focused on people's first experience of microbit being success rather than failure, which is really, really common in computing, actually. So this device abstraction layer was built for the microbit project. It's now actually used in a lot of other areas. The Microsoft MakeCode team use it for MakeCode Arcade, which is an arcade gaming platform they've got. Circuit Playground Express runs Codel as well. So it's a really nice example of an open source project which has grown well beyond the original project. It's written in C++. There's a strong inheritance model, and it uses an event bus. So basically, in order to make it responsive and reactive for the user interaction on microbit, almost everything that happens on the microbit either generates an event or handles an event. And so for embedded programmers, that can be quite weird because we're used to passing around callbacks and or doing things on interrupts, right? But running children's code in interrupt context can be extremely dangerous. It's very easy to lock up the board. So this kind of gives you some of that reactiveness of an embedded system, but without some of the risks of doing kind of bare metal embedded. And we have this lightweight fiber scheduler, which makes a lot of that possible. I think I've talked about it, but it's nice to think about how they work and why I think they're so important for the project. The key editors for the microbit are web-based. So one of the early challenges that we had as a partnership trying to build a kind of embedded product for education was that we knew, if the microbit was successful, you'd have 1 million devices in the UK, in UK schools. And if all the kids logged on at the same time, 9:30 to do their coding lesson, first thing we'd have to do is compile, maybe it's only 10,000, maybe it's 50,000 C++ programs to run on an embedded device right away. And the kind of infrastructure for that is non-trivial. And furthermore, in order to have a compile service, if you don't want to install software on the computer, right? If you don't want to install software locally, which was absolutely out of the question because of the kind of complexity and the diversity of infrastructure in schools. It's great if you want to run an embedded device to install software locally if you own your laptop, but if you're a kind of teacher, sometimes in the UK, just even getting websites unblocked can be hard, let alone installing native software on your system. And maybe people have got Chromebooks. 30% of schools in the US are using Chromebooks now, and there's not really native software in any real sense on a Chromebook. So web was essential, and so we had to solve this problem of how do you get code on an embedded device. And the first kind of real solution was to use a MicroPython interpreter. And we now take the interpreter and concatenate it with the interpreter blob and concatenate it with the user's script in the browser. And inspired by what MicroPython were doing, the MakeCode team thought, well, maybe rather than an interpreter, we can, because MakeCode is not an interpreted language, it's kind of blocks and JavaScript, it's a compiled language. They built an in-browser compiler. So I'm going to cover a little bit about this. So this is probably my most technical slide. So if you're looking at this going, then if you make it through this, then everything's going to be easy from here on in. So let's start with these numbers, ×1 and times millions. So there's something you have to do kind of once every time you update any of these components, which is build all of these kind of C++ low-level components with a tool called Yotta, and GCC is a common open source embedded compiler for everything. And what you get from that is what we call a kind of shell hex file. It contains all of the abstraction layer we talked about, that microbit Codel from Lancaster University, but it doesn't contain anything of the user's program. It's basically just a big jump table. It's all of the key functions and a kind of index of where to find them. And then in the browser, what we do is we take the student's script and we generate JavaScript from their blocks. And then we with an in-browser compiler, generate ARM assembler, an ARM binary, which we combine with our pre-compiled binary, which we just sent over the website like a normal file, almost like an image, combine it and download that to the microbit. And the genius of this is that you need to do this once, and then you can do this millions of times in the user's browser. So it scales really effectively. It means that if 1 million people log on, it really has very little difference to if only 1,000 people log on. And that's a nice time to say that this month was a month where we had more than 3 million sessions in a month, and 1 million of them were unique sessions. So we see really huge usage of the microbit around the world. The other kind of technical detail that I want to delve into is this interface chip that we talked about. So I said there was a dedicated USB chip. And that is another key aspect, I think, of what that makes microbit so effective and so easy. Because when I plug, the microbit is not actually a USB drive. So if I switch to my, this microbit drive here, there's a file on here, details.txt. There's an HTML file as well. There's not actually, this drive, if you were to get information about it, would say it's an 8 megabyte drive. There's not 8 megabytes of storage on the microbit. And when you drop your hex file onto this drive here, what's actually happening is that the hex file is being sent over USB to this DAP link chip, or this interface chip. And that is reading line by line, literally line by line, the file that comes down, and using a serial wire debug, which is the debug interface, to program the target microcontroller, the chip that the student's code runs on. So the microbit actually has 2 microcontrollers on it, but only one of them is ever really exposed to the students for their code to run on it. And the other one we can think of as a utility. It's a tool, and we can upgrade this code. And one of the things we did in 2018, 2019 was upgraded this to allow, actually, rather than just a drag and drop connection, also a direct connection between the browser and the microbit. So you can click download in your browser and the code goes straight onto the microbit. That's with a technology called WebUSB. But it's the fact that we've got 2 chips and this kind of separation of concerns that has made, I think, is one of the things, at least, that's made microbit robust and easy for teachers and kids to use. And finally, I think there needs to be a huge amount of credit given to the team at Microsoft for what they've built in MakeCode, and a full simulator of the microbit device in JavaScript, which I showed you earlier. So this means that you don't need a physical device, but it also means that you can test your programs kind of for logic errors before you run them on the microbit, and you can get some really instantaneous feedback about what they're doing. And I think, one of the things is that this showed me is it's actually incredible working with compiler engineers, because they see computing as a different set of challenges, and it makes it, working with the kind of compiler team inside Microsoft has been really brilliant for the microbit project. Okay, so I think, yeah, that's simulation. So I think it's worth having a little bit of analysis. Does anyone have any questions on the how it works before we jump into this section?
You're doing great, Johnny. I think we're all with you. You're keeping us all together, teachers and techies alike.
Thank you. So obviously, if you're doing something, we're a not-for-profit. The Micro Education Foundation is a not-for-profit, and if you take away the yardstick of money and you're not measuring yourself by how much, how many you've sold or how much cash you've got or what you've delivered to shareholders, then you've got to know why you're doing something, and you've got to have a way of measuring it. And the thing that we think is really important is the impact the Microbit Foundation has. And so we understand this in a number of ways. We look at case studies, we collaborate on academic research, and we look at reporting and awards. So we've got an impact section on the website, which I showed you earlier, and that kind of tells you about kind of evidence about why Microbit works. We try and recognize some of the work that goes on in the kind of global community. We talk about what the foundation has achieved, and we also kind of give insight and context for new programs that are starting up. So I really recommend you have a kind of look at that impact section. And I pulled out some kind of just some nice highlights from the 12 case studies that have happened. And these have happened in really diverse places. So Microbit has had significant rollouts in the UK, Uruguay, Lithuania has been more of a pilot. Denmark, Singapore, and Canada are probably the most significant Microbit rollout. So yeah, UK, Denmark, and also Norway now as well. So there's a kind of range of different. In almost all of these projects, the Microbit has been deployed in a different way, with a kind of different set of programs. Is it teacher training? Is it delivered with families? Is it straight into schools? Is it a computing curriculum, or is it delivered as part of the wider curriculum? So these were just some really nice quotes that cover some of the things that students and teachers have said about the Microbit. And I think one of the things that sticks is that it helps people understand the power of programming, what it can do. I think this is really important to us, that we think that we're giving people an insight into being connected to part of a larger global community. This is not just them on their own. And again, the kind of feedback that there really is a driving of inspiration and removing of barriers is something we think about a lot. So there is some kind of more concrete research behind this as well, rather than a bunch of nice quotes. So the original BBC project had a research, not a university research study, although there has since been a number of academic publications, including from King's College London. There's a woman called Sue Sentence that's done a lot of academic research on physical computing and then the microbit, and the paper that Jana referred to at the beginning as well in CACM. So we're in every project we do now, we're making sure there's a lot of kind of increased amount of research and collaboration on research. So just covering the methodology a bit, we use a bunch of different ways to capture the research. So some surveys, both teachers and interviews with them, student surveys, we look at anecdotal evidence, and then we also get a lot of data from the way people are using the editors. We're obviously extremely cautious about the sorts of stats we get. One of the other things about the kind of compilation in browser, which is fantastic, is that we don't have to send the children's scripts to any server to be compiled. Everything happens in the front end. So we want to be really careful about not taking children's data and sending it to a whole bunch of different services or over analyzing that. But we do need to look at certain statistics just to give us a measure of impact. So we kind of look at the way people are using the device before and after, how easy people found it. I think really important is whether people continue to use the microbit. It's really common when you do a kind of program like this and introduce something new that people go, yeah, you know, that was great, it was really fun, but whether they're going to continue, I think, is a really important part of whether the program has got long-term value. And so these were some of the really nice results. These come from the original BBC research study. So 99% of teachers agreed the microbit made lessons and activities enjoyable for students. So that's a huge, huge win. I'm not going to call out all of these, but I think these student attitudes are really important. So 87% said it helped them learn more about coding. That's a really fantastic percentage. And I think exciting and fun as well is not something that really is historically associated with computing for 88% of students. You know, there's always a small percentage that think it's fun and exciting, but not such a breadth. And then I think my favorite stat from the UK initial research was a 70% increase in the number of girls that said they would choose computing as a school subject after using the microbit. And that, I think, is a really fantastic outcome. Some more recent work, which a more academic study. So this was exploring a pilot in Finland, 100 teachers, 2,000 students. I think this one, 80% of people said anyone could learn programming. I think that's a really interesting result because it's good for communicating, not just well. So for me, I'm comfortable if students don't say I want to be a programmer, but they go, do you know what? I could be. I know that is a thing, in the same way that I have not chosen to be a writer, or actually I couldn't be a writer. That's a little bit more complicated. But there are lots of jobs that you understand. You go, you know, if I really pursued that, there's nothing magic in there. Having kids understand that computing is not magic, it's not crazy, it's a thing that they're going to be able to understand and get their minds around if that's what they chose is really good. And I think as those students that now know that anyone can learn programming go into start organizations, lead companies, invent new industries, the fact that they have that grounding and know that programming is something that they kind of have mastery over is really important. Katie, this is your data about what's going on. So I wanted to put in some stuff about what's actually happening in schools locally to all of you.
Absolutely. You know, I'm here in the chat. We're just all chatting away over here, Johnny. This has been a great presentation so far. So I basically just wanted to highlight a couple of projects in New Jersey with the microbit. Just a quick search online and across social media, you do find professional development, standards aligned lessons to New Jersey standards, as well as outreach, especially with girls and family outreach. The headline for me really comes from the Department of Education in the state of New Jersey, looking at computer science vision, which is about rallying together the troops, families, district boards of education, community stakeholders. All of us have a part to play in helping to establish an equitable approach to computer science instruction. And so just in the chat here tonight, I made a couple notes. Rosanna was sharing about her 6th grade course where her students are programming with using radio, to get their microbits to talk with each other. Daryl's program at Warren Hills High School with girls coding with girls and coding with kids program. They have high school students working with elementary school students, and those role model programs, research shows, are one of the most powerful approaches in the world to help really, especially girls, get excited and feel confident with computer science. And so I would love to brainstorm more with all of you. I'm speaking in the chat right now. We're brainstorming about PBS. We're brainstorming about a whole lot of things here. So my role is I look after the North American ecosystem for the Microbit Foundation, and I would love to talk with any of you or all of you more about ways to bring Microbit more into your community. So on the next slide, you'll see my email address there. Please don't hesitate to reach out. I am a former middle school STEAM teacher and have worked now with almost 4,000 teachers across the US and around the world to integrate computer science, physical computing tools. Have loads of ideas, would love to get creative with you. Don't be afraid to reach out at any time. And I'll go back into the chat now and we can keep talking there. Thanks everyone.
Katie. I just wanted to highlight, as well as the kind of what's going on in research on kind of effectiveness, we also try and do research about pushing the microbit, how far we can push the microbit and how the microbit kind of works. So this is just to pull out a few things. This was a design of a megabit for a kind of a large teaching aid to hold out at the front of the class, which a bunch of students in London did. This is at Oxford University. They used a microbit and a neural net and an optical mouse sensor to recognize handwritten characters. So that's probably the most technically advanced use of 16K microbit that I've seen. And then we've got this page on the microbit tech site, which is for anyone to kind of put, if you've done any research with the microbit and you want to tell the world about it, we'd like to kind of have you add it to this page. And if you are at a university and thinking, actually, I think we could use this device and we could do some is it fourth year undergraduate PhD projects on extending the capabilities of the microbit hardware or researching about future stuff, I'd love to talk to you about the way you can do that, because so much of what's good in microbit has come out of university research and industrial research over the kind of last 5 years. Right. So I promised you some reflection and some analysis about what makes microbit effective. And I think some of these are things that are kind of very much still real live topics. So in the Microbit Foundation this week, we've been talking about a presentation that was given by a researcher through the Raspberry Pi Foundation on the impact of blocks versus text. So this is really an evolving area of research. But I wanted to call out some of the high level important kind of things that we see as being different that I think there's a broad consensus about. So using blocks to teach code certainly simplifies the introductory programming experience. And one of the main reasons it does that is because it reduces the range of possible errors that people can make. So in this little video I've got here, I've got some examples going around of things you can't do wrong. So you can't accidentally put a string into this if comparator because you've got the shapes that tell you what kind of fits where, the difference between a Boolean and a not Boolean value. So, or a Boolean or a string and that other kind of value. So these fit because they're rounded. Oh, we're going back. This one here is a rounded one. It doesn't fit into this box. It fits into this one, but it doesn't fit into this one. So I can't make that kind of type error. You can't make syntax errors because you can't type. You can't make typos. And the structure of the program is really visible to people. So that's a really important thing. And then secondly, we've got that it makes it a lot easier to explore all of the things the device can do. So in here, we've got all of the things the microbit can do visible to you right away, and you can just browse it and find out what you want. So that's huge, and this really deserves the credit to the Scratch team and Scratch for kind of pioneering this approach. On the other hand, there are certain things that you can't do in blocks, and so in the MakeCode editor, there's this fantastic transition between text and blocks that goes both ways. And I think there's been things that go one way for a long time, but the Microsoft team deserve a lot of credit for building something which actually really goes two-way. You can change the code and switch back, and that's, I think, really valuable for people understanding and progressing beyond blocks. so we're kind of doing some research at the moment about the way to improve that transition and make that really clear to people. This is one of the observations that I think Lancaster University have always really championed and makes a huge difference for microbit, and that's this orthogonality of features. And the lesson here came actually from the Arduino world, where this is much more difficult. And the example I've got is almost the one bit of the microbit ecosystem where this doesn't work, and the one place where we didn't manage to get orthogonality is one place that we see kind of pain. So it's kind of counterexample. But what we aimed for on the microbit was that if you could have a block, you could take someone else's code which used similar blocks and put them into the same program, and they would coexist. And this is rare for embedded hardware, because typically you've got a constrained number of resources. Is that on-chip timers, or is that kind of peripherals for talking over serial? There are some real constraints about what the device is capable of, and thinking about the way we will share them in code and the way the concurrency will work, so that if you take an example A, example B, and you try and compose them together, you don't need to do more than just take the code from both of those examples to make it work. And that's been really important. So, playing sound doesn't mean you can't also drive a motor, or putting something on the display doesn't mean that you can no longer use the buttons. Those are things that are actually real in embedded projects, but we've managed to take out of the microbit. And the other thing that I think is really significant is the idea that, well, actually not significant, but an interesting area of reflection for us on having kind of spent a while on this project, is that we have two very different paradigms for programming the microbit. One which is entirely event-based in MakeCode, you've got a program like this, and one which is not event-based at all. It uses this loop constantly polling the buttons. And these lead to very different kinds of programs and very different experiences of programming. And in the interest of just open reflection, I think I'm still at the point of trying to understand what the upside to teaching each of these is. We certainly see this event stuff is people take to it very quickly. It makes sense for user interaction programs, but it kind of hits a limit when you're trying to make complicated games where buttons can do more than one thing, or when you kind of need a main loop for your game. So we're, as a reflection and just kind of sharing some of the things that are on our minds at the moment, understanding the differences between these models and how we maybe can blend them or help learners pick and understand those differences without confusing them is really important. Right, I haven't left myself very long to talk about microbit v2. So I'm going to move on now to talk about, this could have been all I talked about, but I thought it might be more interesting to talk about, one of the key things about microbit v2 is that it is just a BBC microbit. When we set about making BBC microbit v2, we said it must look like a microbit, it must feel like a microbit, it must behave like a microbit. So everything that the microbit does, the microbit v2 can do. And that it extends even to the fact that if I take the hex file that I created earlier, so in my downloads folder, my microbit program that I created earlier, that I downloaded from the browser, I've now plugged in a microbit v2 to my computer rather than a microbit v1. If I switch over the video. So this is, you'll see this has got the shiny face. Can you see that? Someone nod. It's got the shiny face and the notches. If I drag and drop this same program onto the microbit, I get the same behavior. I get the LED flashing, and the same program is going to run on this device. And these are two different embedded devices with different microprocessors. So the fact that we're running the same, or we've got the same file that runs on both of them, is an interesting and was quite a challenge for us. But it was totally essential to make these two devices the same, because continuity was key in our design. So microbit v2 does everything the microbit v1 does. My slides are lagging a bit here, but also it can make and sense sound, because that was one of the most popular things that people did with the microbit. And it can respond to capacitive touch on the touch sensor. So that logo that you see, which is now nice and shiny, you can touch that and it will respond to your touch. And then finally, it's got enough processing power for some really interesting AI and ML experiments. So this is just having a quick kind of look at what we've got there. Touch sensitive logo, a microphone activity indicator. So just to cover this off, we were really concerned about putting or about the implications of putting a device that was capable of recording into classrooms. And we wanted to be really explicit about what that meant and the privacy implications. We wanted to allow teachers to have conversations with their students about what it meant that a microphone was recording. the kinds of things you could infer by listening. And so we've made it very visible on the front of the board when the microbit is recording with this indicator. And we've got a notched edge connector. This is about really easily attaching conductive thread or twisting wire around, making the microbit easier to use in the classroom. On the back, we've now got a power indicator because the microbit now can go to sleep. If I push and hold the power button, you'll see my light is fading out and then turned off, and now it's in standby mode, blinking to tell me it's in standby, and it's not running. If I push the buttons, nothing happens. I'm just going to switch back to me. So, and a speaker on the back, and we can do exciting things with it. So here is a microbit running an ML workload. So if I hold this up to the screen, hopefully you can see that device. I'm not going to say the word yet. If I say this device's name, which is microbit, it smiles. So that's listening to what I'm saying and detecting the words. So if I say cat, dog, donkey, microbit. And so that's running a kind of machine learning model to recognize the sounds on the microbit. Oh,
Johnny, we just had a question come in. I'd like to ask you. Basically, is the capacitive sensor debounced and digital, or can it produce analog samples, for example, to build a theremin?
Interesting. So we've only got a digital pin, but we do have you can get, if you want, with C++, certainly you can get the real data out, but you're not going to get, it's not a kind of classic cat touch sensor. We're running we're actually doing the sensing as part of the display loop. So you'll be able to get something out. You'll probably be able to build a theremin, but it might not be exactly what you'd expect. I'm aware that I'm at time. So that was the kind of last of the slides I had not in the backup material. And I can keep talking for hours more, but I wanted to highlight the last machine learning thing. Is a nice project of making a dance move detector as well on the microbit. Yeah, someone's drawing on the screen. Is that to get attention about a question, or perhaps to alert me to the fact that we are at time? I don't know. Or maybe just not intentional, but I'll clear the annotations.
No, I think we can keep talking a little, or we can take some questions over the audio if you like.
Okay. Yeah, I mean, I was going to demonstrate V2. I think there's one thing I'd quite like to run through very quickly, because it explains why I've got a parrot behind me. And it's just a bit of a kind of closing bit of fun, which was some of the influences for microbit V2. Is that all right? And then do a couple of questions?
That sounds good.
Yeah, okay. So I put together this very short set of slides of influences of microbit V2. So microbit V1, a clear influence, all the amazing stuff people were doing around the world. This is a bit interactive. So does anyone know what these are or who these are?
Cheating as I'm from the UK, but they're the clangers.
They're the clangers, exactly. So these are from a children's TV program, and they can't speak. I mean, or they never speak, at least when you see them on TV. They just make little squeaks and noises, and yet they convey whole narratives and stories with just the squeaks and noises. And when we were looking at putting a speaker on the microbit, we really wanted to do something that wasn't just about, you know, electrical buzzers. We wanted the microbit to have emotion and be communicative. So we took the clangers as one of our inspiration for kind of very simple sounds that were very communicative. We also took this incredibly annoying parrot. This is one of my favorite and most hated things. It listens for a while and then plays it back. And it's terrible and wonderful all at the same time. And luckily you can turn it off. So this was another thing, you know, we thought something fun like this would be a really exciting way for kids to be able to interact with sound. So we're kind of working on making that viable with microbit V2 as well. It was in the design goals for the hardware. This is a graph because I thought I didn't have enough graphs in my slide deck for a kind of technical audience. This is about what the speaker can actually do. The microbit speaker is small and not very expensive, and so we're really good in this kind of frequency range, which happens to be exactly the right frequency for birds and bird song. So we spent a lot of our time thinking about how the microbit speaker could be used to kind of make things that sounded like bird song. And lastly, lastly on the sound influence of the Hitchhiker's Guide to the Galaxy, there's a bit in that called the Shoe Event Horizon, which is about how, well, it's complicated. But people's shoes led to the demise of a civilization. And there's some really beautiful sound work from the BBC Radiophonics workshop in that that kind of is very engaging. And then this conference phone was our influence for the microphone indicator, which you can see here. And we were looking for really good UX for showing microphones on hardware. And smart speakers, you know, the kind of AI, ML, the way those are really penetrating people's lives now, that these are things in everybody's home, perhaps reaching the kind of level of pervasiveness of phones. And we really wanted microbit V2 to be able to communicate to kids how these smart speakers are working. So one of our challenges that we've set ourselves for the future is how do we, in the same way that the microbit has unpacked and kind of made the phone tractable and understandable, how can we use the kind of machine learning capability of the microbit to do an experience that makes things like the smart speaker just as understandable? And really, we're right at the beginning of that journey. Releasing the hardware is step one. Actually, this is a royalty-free image that I took. Does anyone know where it is in the US? Can anyone just tell by the landscape before, rather than having to go through to the Wikipedia reference? If you know, send answers in the chat. That's all on the V2 influencers, and I guess, yeah, it'd be a good time to do Q&A.
Johnny, lots of happy people, got a lot of good questions answered in your presentation. That was fantastic. Well done.
I see there's a lot of chat, so I will review that afterwards in case there's anything else, but I'm sure Katie's answered a huge number of things. Are there any questions that we didn't answer or maybe could be expanded on now?
I'm sure some of the educators have some interesting questions.
Yeah.
I saw Bob's hand just went up. Bob K.
Yes. I'm curious about, I like the interaction with the Scratch type of blocks. We had Mike Resnick here a few years ago and talked about the work going on at MIT. I'm wondering about any interaction between Microbit and the Scratch project and the work at MIT.
So you can use the microbit as an extension for Scratch. We were one of the first extensions that they kind of prototyped. So you can put the microbit, you connect your microbit up to your computer. It actually uses Bluetooth, so it can be completely wireless. So you can have your microbit, and then you get a new set of blocks in Scratch that allow you to interact with the whole existing Scratch universe, but using the microbit as both input and output. So you can respond to the buttons. So you can do stuff when people push the buttons. You can respond to the microbit being thrown up in the air. So the Scratch team have a lovely example where you attach the microbit to a teddy and then throw the teddy up in the air and mirror what's going on for the teddy on the kind of Scratch visualizer. So there's a whole host of ways and very creative ways that you can use kind of Scratch and microbit together. I guess one way to think about it is, you know, in its simplest, the microbit becomes an input device that can cause events to happen inside Scratch. But actually you can put stuff on the microbit display as well. So it's much more two-way and interactive than that. But we describe it as a tethered experience. So, you know, you're still connected to the computer and you're still running Scratch as Scratch, which I think is really important for, you know, Scratch has this incredible ecosystem of resources and sharing. And so, you know, what the Scratch team wanted to do with microbit was create something that was in line with that rather than kind of across it and in conflict with it. So it slots really nicely into Scratch.
Okay, thank you. I think this is absolutely terrific. Thank you very much.
Thanks. So Josephine has a question. Have you considered microbit for other populations, e.g. underserved populations, any group unlikely to think I can do this? Yes. So that's a great example, a kind of great place for our ecosystem to get involved, because we as an organization have to focus because we're small and the challenges we have in front of us are just definitely big enough just for the team as it is. But there have been some really nice applications. So one group that I think I really have enjoyed seeing the work of is working with refugees. So getting refugees to teach each other coding with microbit and using it as skills development in refugee camps, and that happened in Greece. And then in Singapore, where the microbit was deployed, they took a whole family approach. So they also brought in grandparents and parents of kids to all learn together. And I think that was another really interesting approach. I think I'm probably not doing justice to the range of things that people have done looking at other populations. But for now, the foundation well, not unfortunately, I think fortunately is very focused on education, because if we weren't very focused on education, we probably wouldn't be doing as good a job as we could of that. But we're kind of inviting other people to take on the device and put it into other areas.
And you can check out the impact area of our website for more stories of how we are working in communities around the world. Also, I'm curious about that photo that you took. Was that from the Southwest? I saw what looked like sagebrush. I'm thinking Southwest, maybe Oregon, could be a little bit north. I recognize the plant life, but that hill is so well worn. It's old. It's an old area. I don't know.
I'm going to have to follow up with you. I'm going to have to get the high resolution one and look at what that sign says. But my image permission probably is a link to the author on Wikipedia. So let's click through.
I also just hope everybody, oh, Nevada. Yeah, Chris, I was thinking the same thing, somewhere around there. By the way, it is almost midnight where Johnny is, and possibly also Chris. I'm not sure exactly where you are, Chris. Johnny, I think, has done an amazing job for a long day and a great presentation. Last call for questions or comments.
So Neil says, are the V2 units readily available in the stores? They are available. I'm going to pause on readily. I think that I can assure you that we are manufacturing them as fast as we possibly can. So they are not, try a few different places. We've added a filter on the buy page on microbit.org to select V2, and you can have a look at the different resellers that that cover these things. I'm really happy to, like, I'm not going to sleep for a while now after talking to you all, so I'm happy to take questions while I'm still awake. But I'm also happy to wrap it up there if people are feeling like it's time to end.
We'll just take a couple more questions and sign off.
Where are they being manufactured? In Shenzhen. So we are partnered with a group called Premier Farnell, who manufacture them at a company called Mbest in Shenzhen. So there's a there's a kind of factory there that does kind of depends, but we can do about 10,000 in a week. No, a day. But we don't always run at full capacity. Someone saying, I wish these had been available in junior high school. I don't know how long ago you were at junior high school, but you might have had quite a different thing back then. I think there's been some, at least even since I was in school, lots of technology development that makes this, quite a different kind of device. But I actually think there's an interesting, I think we'll look back and almost see lost years of computing education now that we've got, I hope there aren't another set of lost years, but now that we've got back to really teaching computing, I think we'll look at kind of, at least certainly with a UK focus, that kind of period from 90s and 2000s as a period where we weren't taking the responsibility to teach people about what the world was going to be like seriously. Hopefully that isn't the case everywhere around the world.
Okay.
Great.
I think we'll call it quits there.
Deborah just raised her hand, Dennis. I'm sorry to interrupt. Deborah was trying to get your attention.
Oh, all right. And Josephine too. So let's take a couple more. Let's go Deborah first.
They might have been waving goodbye. I don't know.
No, thank you so much for asking. I was very hesitant to ask because I don't usually want to until after I've played with the device and looked at the ecosystem. But would you say that the community is pretty active in terms of developing different hardware and software extensions and ecosystems and interactions?
Yeah, so I would say there is a really active community. I would say we've got a few different facets to that community. So there's a kind of university-led group. So there's a guy called Ben Shapiro, who's not the Ben Shapiro that you might know from Twitter, but Ben Shapiro at Boulder, Colorado, who does a lot of interesting research around kind of interaction accessories, how you can extend the microbit. There's a kind of very big community of people, many of them in Shenzhen, actually making accessories for the microbit and exploring what the hardware can do and doing kind of software support. And then we also have a kind of more globally distributed educator focused, whereas I think a lot of more education focused distributors. So there's a company in the UK called Kidtronic who were part of the original project. They're very focused on selling things to schools. You know, they before they worked on microbit, they sold laser ply material and laser cutters to schools, and they've kind of moved into this. So there's that community as well who know schools and classrooms and are selling kind of kits and other things. So there's a bunch of different areas, and the best place probably to engage with that is in the microbit community Slack channel. So start on the tech site and then jump into the Slack channel. It oscillates. We just had a kind of an event called Microbit Live Virtual, which was really like a kind of incredibly inspiring, people from all over the world doing lots of different things, and that led to a big burst in activity. And then probably in a little while over Christmas, it'll be very quiet, and then there'll be another burst of activity. So that's a kind of a community area that people jump in, but don't expect too much straight away.
You answered the question very well. Thank you.
Right.
Let's let Josephine ask one more question here. No, she's just waving.
I
Okay.
think Josephine was waving goodbye. That's
All
anyway.
right. All right.
Oh, someone did just ask, how do you tell the difference between versions? I will just show that because it is important. The touchable face is one thing. So if I hold 2 up here, so the touchable face, and on the back, they look really different. So on the back, you should be, I don't know which camera, am I holding them up to the right camera?
Yes.
Hopefully.
Yes.
So
So,
yeah, you've got a little
I think
version number, which I'm covering.
Johnny,
with my
don't you think the easiest way to tell is by the notches on the bottom? If you're just
Oh, yeah, probably. Yeah. Sounds about right. Maybe it is midnight here. Yeah, the notches are good. I think the face is the one that stands out to me, unless you happen to have a yellow microbit, in which case we did genuinely talk about getting rid of the yellow microbit now that the face is so similar, but we need to find another color to replace it with. But yeah, notches, face, and then there is a version number written on the back as well. Now it says V2 on the back.
Okay.
Thank you very much for having me, everybody.
Thank you, Johnny. Wonderful, wonderful talk.
Okay.
Have a lovely rest of your evening, everybody else. Bye.
You too.
Thank you, Johnny. Bye-bye.
Bye-bye.